In this lesson, we're going to take a look at graphing the reciprocals of quadratic functions using Desmos. And you can do this with a TI-83, but it's a lot nicer with some graphing software because you can set up sliders and you can identify points much easier. So what I've done is I've set up a function f, and I've written the quadratic in factored form. So x minus r, x minus s, and r and s are therefore the the zeros, or the x-intercepts. And so right now I've got s set at -1 and r set at -4. And you can see that's exactly where the red quadratic crosses at -4 and -1. And I can move this around and it changes the parabola. So I can have zeros of -1 and 2, for instance. And we're going to examine a few different cases. We're going to examine one case where we have two zeros, and we'll look at both options where the parabola is facing up or facing down. And then we'll look at the case where the parabola or the quadratic only has one zero. In other words, it comes down, touches the x-axis, and goes back up again, or vice versa, comes up, touches the x-axis, and goes back down again. And then we're going to look at the case where it doesn't cross the x-axis at all. So where it does cross the x-axis, we're going to see the same behavior we saw with the reciprocal functions of linear functions. When the quadratic becomes 0, the reciprocal doesn't exist. And we're going to get a vertical asymptote at that point. So it's very important to be able to identify the zeros of the quadratic so that you can identify both the domain of the reciprocal function and where it has vertical asymptotes. So let's take a look at this reciprocal function. So I've graphed it here as y equals 1 over f. And some of this looks pretty familiar. We see the same sort of shape on the left-hand side and on the right-hand side that we saw with linear reciprocal functions. But in the middle, this is a little bit different. So on the left-hand side, as we go further and further to the left, the reciprocal function is getting closer and closer to the x-axis. And then as you're moving right, the quadratic in red is getting closer and closer to 0, and the reciprocal starts to get bigger and bigger. And then as you get close to -1, x value of -1, where the quadratic approaches 0, the reciprocal function blows up and heads up towards positive infinity. And we have a vertical asymptote at x equal to -1. Now on the right-hand side, we see very similar behavior. This time the vertical asymptote is when x is equal to 2. In the middle is where we see something a little bit new. You can see there's a loop, a part of the quadratic function that dips below the x-axis, but it doesn't go down too far. It only goes down to a little bit below -2. And so if we can identify that vertex, and remember the vertex is going to be exactly halfway between the two zeros, so exactly halfway between -1 and +2 is a half. You can see it right there. That's our vertex, a half, and -2 1/4. The reciprocal of the y value there, and -2 1/4 is -9/4. The reciprocal of that is going to be -4/9, and that is -0.444 repeating. And so that's exactly, those 2 points correspond exactly in terms of the lowest point there of the parabola is the highest point of that middle section of the reciprocal function. So this is really important for when we go to write the range, because the reciprocal function has 3 branches. The branch on the left and the branch on the right have the same range. They go all the way from 0 up to positive infinity. They don't quite ever get down to 0, but anything greater than 0 all the way up to positive infinity. Whereas the branch in the middle goes all the way down towards negative infinity, but it doesn't go all the way up towards 0. It only gets up to the reciprocal of the y value of the vertex of the parabola there. And since the vertex of the parabola only gets down to -2 1/4 or -9/4, the loop in the middle on the reciprocal function only gets up to -4/9. So it's going to be important to be able to identify the y value of the vertex of the parabola. Let's try moving this around and get slightly different values. So what if we go from -2 to +2? In other words, we have zeros of -2 and +2. Then we know the vertex is going to be halfway between, which is at 0. And sure enough, there it is at 0, -4. And the reciprocal of -4 is -1/4. So we get a corresponding maximum of that middle branch there at 0, -1/4. What happens if we stick a negative sign in front of the two factors? Well, now everything just flips, and we get, we lost the vertex there. Let's put it back up here. So now we get the two branches on the left and right heading down towards -infinity and heading up towards 0 from below. And then the loop in the middle, the branch in the middle, goes all the way down, but only to 1/4. It doesn't go all the way down to 0. And so there are y values essentially that are missing from the range, right? We don't have any positive y values between 0 and 1/4. And so when you go to write the range of this, you're going to have to be aware of that point, where that point is. All right, let's take a look at the case where we only have one y-intercept, and that will occur when the zeros are essentially the same. So if I move S here, the slider, over so that it is 2, you can see that this has a vertex at 2, 0. And so, not sure why these are identified here, but we can see that now there's just two branches. We have one vertical asymptote, which corresponds to x equal to 2. And on the left, the reciprocal functions starting at 0 and heading down towards -infinity. On the right, we get the exact same thing. Since the quadratic is never positive, the reciprocal function is never positive either. And so we don't have any positive y values. And the range is just simply all negative values, anything less than 0. If this negative sign out front is eliminated, we can see this just flips up. And so now we have the mirror image of what we just saw. Let's try a different set of zeros there, 3 and 3, for instance. So now again, we just have the one vertical asymptote, and the two branches on the left and right are identical. Now, what if the two zeros were really close to one another? I'll just move this over a little bit. It sort of looks like the same scenario, but we really do have two zeros. And therefore, there is a little branch in the middle because the quadratic has some negative values. You just can't see it. And if you go down far enough, you can see it. And sure enough, if we find the vertex here, which that looks about right, yeah, 3.31 and -0.096, that's going to correspond to the peak of this reciprocal branch. And the reciprocal of the y values, you can see this is about -1/10, and this is around -10. So sometimes you won't necessarily see that middle value or that middle branch, but it's still there. As long as the quadratic has negative values, you know the reciprocal has negative values as well. All right, so now let's take a look at the final case, which is when the quadratic doesn't cross the x-axis at all. And for that, we're going to have to take a look at a different way of writing the quadratic. So I'll define this as, let's say, x squared plus some value, a, let's say. And I'll add a slider there for a. Okay, so now we don't get any holes in the domain. We don't have any vertical asymptotes because the quadratic is always positive. Or if I stick a negative sign in front of it, it's going to be always negative. But in this case, the quadratic is always positive, we still have to pay attention to the vertex, because the vertex is going to tell us something important. If we go far enough to the right or far enough to the left, the quadratic is heading up towards positive infinity, and so the reciprocal function is heading down towards 0, and so we're still going to have our horizontal asymptote of y equals 0. And then right where the quadratic comes down to the vertex, the reciprocal function is going to come up to its maximum value, which might not be too much depending on what the vertex is. And you can see here with a vertex of 0, 2, the reciprocal of 2 is a half, and that's exactly the maximum point of the reciprocal function. So it has a very, very limited range. If we bring the parabola down closer to the x-axis, let's say we bring it down to about a third there, let's say, 0.33. So this now, the parabola has a vertex of 0 and roughly a third. The reciprocal of a third is obviously 3, and you can see that the reciprocal function gets a little peak. It goes right up there to the reciprocal of 0.33, which is just a little bit over 3, and then it heads back down again. Again, there's no vertical asymptotes here. There's no holes in the domain. If I put a negative sign in front of this, initially that's not going to be entirely below, so I'll have to change the a to negative as well. And so now again I see the exact same sort of behavior that we saw when it was positive. This time though the reciprocal function is entirely negative, and the lower this is, right, so for instance there when the a is negative 10, the maximum value there of the parabola is when the y is negative 10, and the reciprocal of that is negative 1/10. And so the reciprocal function is not going to look that different from a straight line. It's going to have a tiny little deviation as we get closer to 0, and it's going to drop to a minimum of negative 0.1. When it's, let's say, negative 1, you can see that the two functions meet, which is always the case for all reciprocal functions. Whenever the y value is negative 1 or positive 1, they cross. And so here the vertex of the parabola is negative 1, and sure enough the reciprocal function comes up to meet it and has a minimum value at 0, negative 1.